Think about the very core of every atom, the nucleus. Protons tell you the element, okay, but neutrons, they're often seen as the glue, right? Stabilizing things, making isotopes.
Exactly.
We all know hydrogen, simple, one proton. Add a neutron, you get deuterium. Add two, that's tritium. But it makes you wonder, doesn't it? How many neutrons can you actually pack onto just one proton? I mean, 5. Is that even possible?
That is the fundamental question, really. How many neutrons can bind? It's central to nuclear physics. And hydrogen, being just one proton, it's the perfect test case for studying the strong force, its limits.
Right.
We've seen hydrogen with 3 neutrons, 4.
Right.
That's hydrogen 4. But when you get to the really heavy ones, like hydrogen 6, OH, or even IH, well, things get fuzzy.
Fuzzy how? Like hard to make or hard to measure?
Both, really. Their existence, their properties, they're much harder to pin down. There's been a lot of, let's say, debate, especially about hydrogen 6.
Okay.
For a long time, people couldn't agree on its ground state energy, basically how stable it is.
And that brings us to this new research, which sounds pretty remarkable. A team, the A1 collaboration in Mainz, Germany.
That's right, working with partners from China and Japan, too. Fudan University, Tohoku University, University of Tokyo. A real international effort.
And they've managed to not just create, but actually measure this hydrogen-6 for the first time using this specific method.
Yes, using a really innovative electron scattering technique. It's quite something.
Okay, so that's our mission for this deep dive then. Let's get into it. What does nailing down OA actually tell us about, the rules of matter, especially when things get this neutron heavy?
Precisely. For decades, we've needed clear data on these super neutron-rich hydrogens. The existing information on OH, it was sparse, sometimes contradictory.
Right, the debate you mentioned about the ground state energy.
Exactly. Was it high? Was it low? This new experiment, it gives us a clear signal. It really helps settle that.
Okay, so how on earth did they do it? Getting 5 neutrons to, hang out with 1 proton sounds incredibly fragile.
It absolutely is. And the method they came up with is, quite clever. They used the Mainz Microtron Accelerator, MAMI.
MAMI, okay.
And they fired a high-energy electron beam, 855 megaelectron volts, so quite powerful.
At a lithium target, lithium-7.
Correct, lithium-7, and it happens in basically 2 steps. First, an electron hits the lithium nucleus and gives energy to one of the protons inside.
Okay.
This energized proton, it essentially breaks apart almost instantly. It spits out a neutron and another particle, positively charged pion.
Got it. Electron hits proton shatters, releasing a neutron in this pion thing. So where does the hydrogen-6 come from?
Here's the really neat part. That neutron that just got kicked out, it then interacts with another proton still inside what's left of that same lithium nucleus.
Inside the same nucleus. Wow, okay.
It transfers energy, and bam, through that interaction, you get a fleeting nucleus of hydrogen-6 formed, plus the leftover bits of the lithium.
Fleeting is probably the key word there.
Oh, extremely short-lived. And the crucial thing is, they managed to detect the electron that scattered off, the pion that was created, and the proton that was involved all at the same time.
All 3, simultaneously.
Simultaneously. Using 3 high-precision magnetic spectrometers, think about trying to track 3 specific, fast-moving objects and knowing they all came from the exact same event. That's the challenge they overcame.
That sounds incredibly complex. Was the setup itself unusual in any way, besides needing 3 detectors at once?
Definitely. Normally in electron scattering, you use really, really thin targets. You want a clean interaction.
Makes sense.
But here, because creating ERH is so rare, they needed more attempts, if you like. So they used a target that was, relatively speaking, quite long and thick. 45 millimeters long, 0.75 millimeters thick.
That is unusual for this kind of experiment, isn't it? Wouldn't a thicker target just muddy the waters with other reactions happening?
It absolutely increases that risk. But, and this is key, the electron beam at MAMI is exceptionally good. It's very focused, very stable, almost like a laser.
So the beam quality let them get away with the thicker target.
Pretty much.
Yeah.
It allowed them to manage the noise from other interactions while boosting the chances of seeing the rare road event.
Yep.
And just working with the lithium itself was a whole other challenge.
Oh, why is that?
Well, lithium is tricky. It's very reactive chemically. It's mechanically quite fragile. And it's sensitive to temperature changes.
Sounds like a nightmare to handle for an experiment like this.
It requires very careful handling, yes. And then coordinating those 3 big high-resolution spectrometers to all work together in coincidence mode, as they call it.
catching all those particles from the same event.
Exactly. That's a rare feat in itself. Very demanding technologically.
So they ran this for 4 weeks. What was the payoff? How often did they actually see this hydrogen-6?
It was an intensive run, yes. And they saw roughly 1 successful event per day.
1 per day. Wow. That sounds low.
It is low, but it was actually about what they predicted. These are incredibly rare events we're talking about, but each one of those detections provided vital data.
And what was the key piece of data? What did they actually measure about teal?
The big news, the really significant finding, was a clear signal for hydrogen-6 at a very low ground state energy.
Low. Okay, so that settles the debate you mentioned earlier.
It points very strongly towards the low energy side of that debate, yes.
Right.
And here's the kicker. That low energy implies that the interaction between the 5 neutrons in that nucleus is actually stronger than our current theories were predicting.
Stronger, so the neutrons are sticking together better than we thought they would in that crowded environment.
That's a good way to put it. They seem stickier in this configuration than the models suggested. And that forces us to rethink some things.
Wait a second. So you're saying our fundamental understanding, our models of how protons and neutrons interact, they don't quite work right when you get out to these really neutron-heavy edges.
That's exactly what this suggests. It poses a real challenge to our current models of these multi-nucleon interactions. Most of our models are tuned based on nuclei closer to stability.
Right, the ones we see all the time.
Exactly. And this result strongly hints that the rules might be a bit different when you have such a massive neutron excess. It's giving us new information that existing theories are, frankly, struggling to explain fully.
Oh, so, okay, why should we, the listeners, really care about this? I mean, it's a super exotic, short-lived hydrogen isotope. What's the bigger picture?
Well, if you connect it back, it really goes to the heart of nuclear stability, the chart of all possible nuclei.
A nuclear chart, yeah.
Understanding these exotic species like OAEAL helps us define the edges of that chart. Where does stability end? How far can you push that neutron-to-proton ratio before things just fall apart instantly?
So it maps the boundaries of matter.
In a way, yes. And maybe more fundamentally, it tells us crucial things about the strong nuclear force itself, the force holding nuclei together. By probing these extreme unbalanced systems, we learn how that force behaves under, unusual pressure. It's not just about one weird isotope. It's about testing our understanding of the fundamental glue of the universe in a new regime. And this finding, this unexpected stickiness, suggests that glue might act differently than we assumed in these neutron-rich conditions.
It's like stress testing the universe's building code at the tiniest scale. What does this mean for future research, then? Where do nuclear physicists go from here?
Oh, this will definitely spark more work, both experimental and theoretical. Other experimental groups will likely try to confirm this using different methods, maybe push towards even heavier isotopes like hydrogen-7, perhaps.
And the theorists.
The theorists now have a really interesting puzzle. They need to go back to their models of nuclear forces and figure out why these neutrons are interacting more strongly in UDH. What subtle aspect are the current theories missing? It really opens up new directions for refining our understanding.
Okay, so just to recap the key points. This international team using a clever new technique at the MAMI accelerator.
Right, the electrons scattering on lithium.
They successfully created and measured hydrogen-6. And the big surprise is that its ground state energy is low, which means the neutrons inside are interacting more strongly than our theories predicted.
Exactly. It challenges our models, particularly for these extremely neutron-rich systems.
Pushing the boundaries of what we thought we knew about nuclear forces.
Precisely. And it's worth highlighting, this work was really driven by a doctoral student, Tianhao Xiao, who led the experiment and the publication in Physical Review Letters.
That's fantastic.
And Professor Joseph Pochizala from the collaboration really stressed how crucial the unique capabilities of the MAMI facility were. Couldn't just do this anywhere. It took that specific combination of beam quality and detector technology.
It really is a testament to both the researchers' ingenuity and the technology. It makes you think, doesn't it, about the absolute limits. How many neutrons can one proton hold? What else is going on in these extreme nuclei that we haven't figured out yet?
What other forces or effects might come into play when you push things this far?
Yeah, it's kind of amazing that hydrogen, the simplest element, can still hold these deep mysteries.
Indeed. And exploring these extremes, it's not just about filling boxes on a chart. It's about uncovering fundamental truths about the forces that shape everything around us. We still have so much to learn.
Absolutely. And we should mention this kind of fundamental research relies on support. This project was backed by the German Research Foundation, DFG, China's National Key R&D Program, the EU's Horizon 2020, the National Natural Science Foundation of China, and the Japan Society for the Promotion of Science.
That international collaboration and funding are vital for pushing these frontiers.
For sure. So as you think about a nucleus behaving in ways we didn't fully expect, maybe ponder this. What are the true limits of matter, and what surprising rules might govern the universe at its most extreme edges? It's a pretty vast and fascinating landscape out there.